the ideal object. Sorry. Okay. Now, hello. Just hello. Okay. Okay. So coming back to this game, we have a two world, O0 and O1. How do we define the distinguishing game? So adversary is the one who is trying to distinguish. Okay. So he will first the one bit will be sampled either 0 or 1 with probability half and half. What it means, basically the challenger is sampling one of the world randomly. The one either real world or ideal world with probability half and half. And then adversary makes some query, some query to the constructions or the ideal oracle. He doesn't know with whom he is interacting because he doesn't know the B. And he obtains the corresponding response. The yi means the ith query. So this is the ith query. So there will be several queries adaptively. So yi is the response of the ith query, but response is given or computed under the oracle OB. So B can be 0 or 1. So it is either O0 or O1. And B is chosen once. Throughout the game, B is chosen once and it will be fixed. Okay. And at the end, after making all the queries, so after all the query response are done, adversary must submit a bit B prime. And the goal of the adversary is to guess B. Right? So that is the goal of the adversary. That means if he can guess B correctly, that means he knows with whom he is talking. Right? So in the AI, like you are making questions to other room, in the other room, either there is a computer or the human being. If it is computer, the computer will answer your questions. If it is human being, the human being will, the person will give the answers. After making several queries, questions adaptively, if you can tell like, okay, I am talking to computer, then and if that is the computer, then you know, like you know how you can distinguish that computer is not good enough to replace human beings. So same thing here, like if the adversary can know, okay, I am talking to the real world, not the ideal world, then the real world is not good enough to replace the ideal one. How do you measure the goodness? Like, so this is a success probability that will be like the probability that A returns correctly, that B prime is equal to B. The B prime is returned by the adversary is equal to the B will be the success probability. Okay. So that is the one way to define the security game. So in real life, what happens? Like, sorry, in cryptography, what happens? We have two worlds, a real world and ideal world. Adversary will either make the query, so adversary will give the query xi, and the response will be the yi, which can be computed on the real world or the ideal world. And there will be several such query and responses, and at the end, adversary will return B prime. And there is another popular definitions, and that is the definition I will actually use in this talk. Instead of the success probability as a measurement, I will try to compute two different probabilities. One is the adversary returns single bit 1, not a 0, just 1. When adversary is interacting with the ideal world, and another probability when the adversary interacting with the real world. So that definition may not look intuitive compared to success probability definitions, because success probability is measuring the probability that what is the probability that you are guessing correctly. On the other hand, there is no such direct connection with these guessing things, because in both probabilities, I am computing what is the probability that A returns 1. But I take a difference. But for example, if A always returns 1, then both probability will be 1 and it will be 0. The difference will be 0. So the main reason to consider this to normalize the success probability metric. So success probability can be always half. I can always make half. I can just make a random guess, right? Irrespective of the query response, I will randomly choose one of them. So I can always make a half. So what we, in general, you want to have a metric. The metric is between 0 and 1. 0 means bad. Bad for the adversary, good for the designers. So if you can make 0, then you have a good design, but bad for the distinguisher. And 1 means very good for the distinguisher. Distinguisher can distinguish perfectly. So this is the relationship between the advantage between the success probability of the adversary and this difference. So what you have to do, you multiply by 2 and you subtract from 1. So that's a simple exercise. I think for all the students who are just learning this thing first time, you must check these equalities. Okay, this equality is very simple. You have to condition on the bit B, which can take either 0 or 1 with probability half and half. So once we have these relations, so we can ignore these success probability things. Okay, and we will concentrate on these two probabilities. And we'll see like how these two probabilities will be for different type of designs. Okay, so now I'm trying to focus on how the distinguisher, how we want to define the distinguisher. So what distinguisher will do after interacting with anyone of the world, he doesn't know whether it's a real world or ideal world. He or she must identify an event based on the query and responses, whatever received. So that event is called the distinguishing event. So that event will depend on your designs. So by looking at the designs, you have to study the designs very closely. You got a design, you study very closely, and you find some event which looks weird in the sense this type of event should not occur in the ideal world, but it is happening for the real world. You have to identify such event, okay? And once you see that the event holds, you return 1, that adversary returns 1, otherwise returns 0, okay? So that will be your algorithm. And then if you can find such an event where, as I said, like the event looks like it is going to happen for the real world with probability 1 or almost with probability 1, but in the ideal world, it's not going to happen, or very close, with very negligible probability, it will happen. Then, as I said, like we have to compute two different probabilities and then subtract. So the one probability is this: the event E holds in the real world, which is approximately equal to 1, and the other probability is the same event holds in the ideal world, that probability approximately equal to 0. Then you take a difference, then you get a number close to 1, and then you are done. You get a distinguisher. Okay, but this 1 and 0 is not that you have to do all the time. You can relax. You can maybe, instead of this is 0, you can make a 1. Yeah, this is 1, you can make it 0, and you can make that 1 or close to half, something like that. Or any two numbers which are not same, which are away, like maybe half and 1/3. That's also okay. Okay, so that may depend on your designs, but ideally we try to have such things. So just a side note, like if I make this to be 0, and this happens with certain probabilities, then we can call that impossible event, right? That event should not occur in the real world because the real world probability is 0. So this also appeared in the distinguishing attack. That is called impossible distinguisher, impossible distinguishing attack. Or in differential cryptanalysis, we will sometimes see impossible differential cryptanalysis. Okay, so the other choices can be very much possible depending on the designs. Okay. Okay, so let's have some specific game. So we understand the general notion of the distinguishing game. Now let us look at the specific game. So the very first game is the PRBG game, the pseudo-random bit security game. Okay. So what serial random bit function does, it is a function which takes n bit input and returns m bit outputs. It's an expanding function where m is much, much larger than n. But it could be like n plus 1 also, but in general, m should be very large. But even just 1 bit extra is also enough, is good enough for PRBG. So any m greater than n should be okay. And what do you mean by the good PRBG? Now is the designer point of view. What if you want to design a PRBG? It should be like it should satisfy this property that whenever we give a uniform distribution as an input to the G, I must get a uniform distribution as an output. Okay, so that means it's like we can use, if that happens, then we can use as a key expanding function. Why? Because we need key to be uniform. That is a general requirement, that key should be uniformly distributed over the key space. But at the same time, we do not want large key. For many reasons, I do not want to memorize the big key, or I do not want to hold the big key. It will be more vulnerable. So just 128-bit key in symmetric key is good enough. We want to keep as short as a 128-bit key. But some algorithm, 128-bit may not be enough. You need more keys. You need 256-bit keys or 1024-bit keys. So then you take the help of G. So G will take your short key and expand to a large key, because it says that if you take a uniform distribution, the output will be a uniform distribution. But if you have some idea about the information theory, you know that this is not possible. This cannot be made. It's impossible to expand uniform distribution to larger uniform distribution. It's not possible. So what we can do, okay, we can again take the help of the distinguishing world. Okay, I cannot get uniform distribution for sure. That's what uniform distributions, that's what from information theory we can guarantee that it's not possible. So, okay, we can get some distributions in the output, means that G of the output, which is m bit, but is not uniform. But is it close to uniform? Can someone distinguish the uniform distribution of the m bits with the output of the G? So we have a two world. The real world will be the output of the G, and the ideal world will be the uniform distributions. And your goal will be to distinguish as if you want to think the attacker. So you just change the role. Sometimes you think that as an attacker, sometimes you think as a designer. So right now I'm thinking as an attacker. So you have to go. Your goal is to distinguish these two worlds. So more formally, we have this bit B. We first choose S randomly. That's your actual key, the original key. And then if B is 0, that corresponds to a real world. Then you compute T as a GS. T is your final key. Okay. But if B is not equal to 1, then you generate the T randomly with from the A. That's the ideal world. Okay. The blue one is the ideal world and red one is the real world. And you give T to the distinguisher. Or the challenger gives T to the distinguisher, and you have to tell whether it's a real world or ideal world. Exactly the same here. There is no such query is coming from the adversary. That is the only difference. We don't have any query from adversary to challenger, because there is nothing input dependent things there. Only the two values, and you have to distinguish them. So you will see there are some games where you need to have a query. A quick check we can to get some idea about that how distinguisher can be defined. I just keep a simple theorem. So if you consider a linear functions which expands from n to n plus 1 bit, where m is n plus 1, then this LK cannot be a PRBG. Do you have any idea? That can you quickly tell me why it is true? Can you identify the distinguisher? Any one of you? So you know, like when you see the designs, there are some non-linear component. Just linear is not sufficient. We have to have non-linear. And the basic reason is this one, that if I just take a linear function as my PRBG, as my potential candidate of PRBG, which is not, you have a distinguisher. Sorry? It is a proper subset. So anyway, so so G of a output will be a proper subset of 0 and power m. So in general, it will be a proper subset because maximum you can get 2 power many output values, right? But yeah, that's true. But now how do we explore that proper subset property? Right. So what will be your distinguisher? At the end, you have to identify a distinguisher. The intuition is right. No. So here there is no query model actually. So that can happen only if you make a query. So you are getting only one output, LK. You don't get LK1, LK2, or LK1 plus K2. That happens actually, I will come to that for the pseudo-random functions, where you can give the inputs and get the outputs. Here only you get only one m bit output. Here m is n plus 1. So you only get n plus 1 bit output. That's all. You cannot make any repeated. Right? Sorry? So we must have to check the dimension, but you get a k plus 1 bit output. You don't. So actually, the input of your algorithm is a k plus 1. Sorry, n plus 1 bit input, right? So you don't get any description in the input. You know say function L. So you can work on L because you know the function L. Probably you know the matrix for the L. You can work on that L, get some nice properties, and then you have to work on the input you receive. The distinguisher should be a function of the input you receive. Okay. So what we can do, because L is a linear function from n bit to n plus 1 bit, you can efficiently find n plus 1 to 0 or 1 plus 1 to single bit such that this will happen for all k. Can you check this? Can you first line is that's the main thing. Like from n bit, you are expanding to n plus 1 bits. Okay. So that means there must be all these n plus 1 must be linearly dependent. You must be able to find a linear relationship between all these n plus 1 bits. And that is what the function L prime is, which maps n plus 1 bit to 0, 1, such that the output of this L prime of Lk must be 0 for all k. Okay. So once you have this, once you you get this, then what the distinguishing event is that given T, the thing you will receive, you compute L prime of, sorry, this is L prime, not L. You compute the L prime of T. You compute the L prime of T and check whether the L prime of T is 0 or not. If the L prime of T is 0, that must happen for real world with probability 1. That is what the first line says. You return 1, but in ideal world, T will be uniformly distributed. L prime is some non-zero linear functions. So L prime of T will be 0 with probability half. So what difference you get? In real world, the event must happen with probability 1. In ideal world, it happens with probability half. So difference is half. Any non-zero difference is fine. So you have a distribution. Okay. Okay. So now I come to the pseudo-random function thing where you can actually have an input. So in the pseudo-random function, what happens like there is a function fk where there is an input, there is a key. See, k is the kappa is the key for the function. So basically, it has two input. One is the key. Another is there is a specific input which is the bit d bit input and returns n bit output. Okay. So you can imagine like a MAC or tag or authentication. Like it has a key, and it takes a message you want to generate the tag, the d bit message, and returns the n bit tag. Okay, that n bit tag, the output of the pseudo-random function should be random looking. So if you change your message just by a single bit, the output of the tag will be a completely independent random looking text. That is what the goal of MAC or the pseudo-random functions is doing. Okay, so this is the real world function. In ideal world, what we want, because it cannot be truly random for every input. So information theoretically, again, one can guarantee that it's not possible, like PRBG things, like you cannot expand the uniformness. Here also you cannot expand the randomness, because only randomness you have the key chosen uniformly from the k bit, and you expect all the n bit outputs for every different inputs are random. too much uniform randomness, random bit you are demanding from a functions just from the k bit random. It's not information theoretically possible, but again, it might be possible in the distinguishing world scenario. So we follow the same rule, like we choose B randomly, the challenger, then you can make a query. Okay, the query is the input, the message, or the for who you want to compute the tag, and then you get the response. The response will be again like if B is 0, then means in the real world you compute the actual way, right? The output of the function f, and in the ideal world you just randomly sample the n bit and give it. You ignore the x, just randomly sample the tag and you give it. You have to distinguish these two things. Okay, so this is called pseudo-random function security game. Distinguishing game for the Mac you can use. And there's a simple observations. This I just want to keep as an observation. You just you can check yourself. Like if you have a PRF, then you can easily generate a PRBG, because what PRF does, PRF actually, if you look at all the inputs 0, 1, 2, 2 power t minus 1, then all these outputs that fk0, fk1, and fk2 power d minus 1 should be random looking output. That is what the goal of the PRF. Because in the ideal world, what happens if you give 0, you get a random y. If you give 1, then you get a random y, and so on. So all these, if you accumulate all these random y, you get a big random strings. That is what in PRF should aim. And I can define the output of the PRBG like this. So I choose the key uniformly, and then the output of the key will be all the outputs of the pseudo-random functions. So I can construct a PRBG from PRF very easily. And we can do the other way also. So you can, if you have a good PRBG which takes k bit or kappa bit input to 2 power d times n bit output like this here, then you define the output of PRF function is particular locations of the PRBG output. So just the reverse of this particular definition. But here you need a big output. I mean at least say d equal to 1, then it needs 2 n bit output. So you need PRBG from, if the k equal to n, say n to 2n bit output. Okay, and there is a result like how you can extend that n to 2n to multiple bits also, means bigger d value. So I just take d equal to 1, then it looks simpler, smaller, but you can easily extend for the other d, and that's a well-known result by GGM constructions, that how to construct PRF from PRBG. Okay, so that's known as a GGM construction of PRF from PRBG. Okay, so there are other two games. Basically, one game, the second one will be very similar. The pseudo-random permutations. That's exactly the same like pseudo-random function. Now the object is not the Mac. Is object is a block cipher. Imagine block cipher. Okay, in the block cipher, what happens? Like you have a say n bit input and you get an n bit output. Okay, and that's the permutations. The key is a kappa is a key which is k bit, which could be n, k can be equal to n. But here the point is that n bit input and n bit output, and that is the permutations. Okay, the block cipher, because you from the hypertext you must be able to get the plain text, right? And remaining is same. Because of the permutations, the ideal world, I have to modify the definitions. The previous case, if you quickly go back to the previous case, the PRF definition, here the ideal world, the y is sampled uniformly from the n bit, but now y is sampled from n bit, but ignore all the previous y sampled. Why? Because I assume here that all these x will be distinct. You make distinct queries. You always give the distinct input. And permutation, you know the property, like if you have distinct input, you must get the distinct output, right? So whatever y values you already have given, you sample outside all those y's, right? To maintain the permutation property in the ideal world. And real world, it will happen automatically. You cannot, because it's a permutation, you don't get two different y which match. If they match, that's called collision. We will use the word the collision very frequently later on. So if two outputs are same, we call it collision. In real world, you don't expect collision from a permutation, obvious by definition. Okay. So again, the advantage definition of the PRP will be B prime is 1 in the real world, and if B prime is 1 in the ideal world, you just take a difference and take the absolute value. And the modified definition is a strong pseudo-random permutations, because in that definition, I am giving access only to the encryption, like the forward queries. But I should give the little bit power to the distinguisher. You can make a backward query also, the decryption, right? So this function fk, is the permutation. So I should give a inverse query. So this x represents the forward query, y represents the backward query. Because I give the notation x for the input kind of thing and y is output. But now your output of the block cipher can be your input. So y could be a query. And in that case, you choose x sample uniformly from all the previous x. Okay, all the previous x already observed by the adversary, including those x which have been queried. So just to maintain the permutation property, whatever you have to do, you maintain that and sample uniformly from whatever possible choices. That's the ideal world. And real world definition is simple. You have a description of the permutations, a block cipher, whatever. You follow the description. You have to follow the description blindly. And at the end, you have to distinguish. Any queries so far? Oh. Oh, no. Audio is not available. ঠিক হয়ে গেছে পরে Oh, now all right. Okay, sorry. Yes, okay. Now all right. Okay, so now I just have one slide for the birthday bound, and then we come to the different examples. Okay, so this birthday bound is so birthday bound security will be the basis of this today's talk, because and it's also very popular in cryptography. So if you have not seen yet, you must, after today's talk, if for the student at least, you should go back home and check this birthday paradox, because this is the very classical basic results we always use in many cases. So very quick recap, what birthday bound means. What, like you are sampling the Q values randomly from the set of n bits. So in the context of the birthday paradox, like if you have 30 students in a classroom, this room is very big. We don't need this large. Even small classroom like 30 people, you look at the birthday of all the people, and with high probability you expect you get 2 persons will share same date of birth. Okay, so the date of birth will be like your 0 and power n. Like from where you sample the date from the date of all possible date of birth, like 365 possible cases. But here it will be 2 power n possible cases. And you sample uniformly and independently different values, x01, x2, x2. Okay. And the collision means that 2 of them are same. 2 persons share same date of birth, right? So one can first calculate the no collision probability. That's easy to calculate. Okay. And then that can be approximated by e power minus q, roughly q squared by 2 power n plus 1. Okay. So at least one collision will be the complement of that 1 minus this. So we can see that what we will use that if the key is close to or order of 2 power n by 2. So this is all this approximation, and I should have written in terms of instead of 2 power n by 2, I could have written 1 by O of 2 power n by 2. This is exactly. So if the Q is order of 2 power n by 2, then at least one collision probability is at something 1 minus 1 by E. So you can make it half also, depending on how little big you want to choose Q. Like you can multiply some constant. So the thing you have to remember, if the Q is order of 2 power n by 2, then you get a collisions with probability, at least with probability half. And you can make the collision probability close to 1, towards close to 1. Then you don't, you have to increase your Q. 2 power n by 2 is not then sufficient. So what you need n times 2 power n by 2. You don't have to go 2 power n to get a collisions. Okay, that much you don't need. Just only thing you have to go the n times 2 power n by 2 is not big. Like, so if you have a n times 2 power n by 2 many sample, then the collision probability will be close to 1, very close to 1. Okay. And the similar result for 2 list. So if you have a 2 list, like here I am looking for a collision within one list. So sometimes what happens, I have another list. So we have a list of X, you have a list of Y, and I am interested to get a collisions between X and Y, not among X or not among Y, collision between X and Y. So my interest of event here is probability of Xi equal to Yj. Okay. So in that case, it will be PQ by 2 power n. The collision probability will roughly be PQ by 2 power n. Okay, P is the size of the one list and Q is the size of the other list, right? So what you have to ensure there is a collision, the P times Q should be order of 2 power n. So one way to make it, okay, both are 2 power n by 2, like the previous case. Okay. Or you can have a one collision, one size is a little bigger, maybe 2 power 2n by 3. The other list is smaller, 2 power n by 3. Then you multiply, you get 2 power n. So you don't have to keep both 2 power n by 2. You could have a asymmetric choice of 2 lists. Still, you can ensure the collision between 2 lists. So these are the 2 fundamental results from the collision you must remember for analysis. Okay. So now I first describe the Davis-Mayer construction. So what it does, you have a block cipher and you make that block cipher. The block cipher is a function for permutations, right? For every key, the M from M to C will be permutations, but I don't want permutation nature because I want to use one possible reason is that I want to generate a tag, okay, like a function, or I want to generate a hash function, the compression function. Okay. So this is the best. This is fundamentally first. This was used to generate a block cipher. To generate a compression function. Okay, the Davis-Mayer is used to generate a compression function out of the block cipher because block cipher is widely available. Whenever someone designs block cipher or stream cipher, right? So these are the widely available, and there are basic reasons for designing block cipher easier compared to designing something non-invertible functions. So if you know some about how we design, like if you look at the AES, you see several rounds of AES, right? So that means so we have 10 rounds of AES. And if you look at individual round, each round behaves like a permutations. So what essentially you are doing, you are composing several rounds of permutations to generate a big permutations, which is a block cipher. Okay, and you expect if you compose more and more, you get more and more security. Unfortunately, this doesn't happen for the function. If you have a function, you generate a function, one good function, and you compose several times, what happens that you are actually losing the security of the function quantum. So that's why iteration is natural choice for the permutations. And we also design the block cipher. And what we do, if you want a function, then what do you do? Okay, first design the block cipher and then design a function from the block cipher in a certain way, other way. And that is one way to design a block function from the block cipher. So what you have to do, you have to XOR the output of the block cipher. So you take a permutation output and you XOR the input. Okay, invertibility will be lost. You can clearly see that given T, I cannot get back M because I want to find M such that M plus the E of M equal to T. So now the function property as a permutation property is lost. Even you may get a collision for 2 different M, I can have a same T. Okay. And but there is one observation you can make that because you design that from the block cipher itself, you know that C for different M, the C must be distinct. And what are the C's? C is the M plus T. C basically M plus T. So you know that M plus T must be distinct. This is for this particular design. Okay. And we will explore that as a event, distinguishing event. So when this Davis-Mayer is your construction of the pseudo-random function design, and in the ideal world, you are expecting a random output, random T. Okay. But you know, if in real world, this Ti plus Mi never repeats. It will be collision free, right? So if you observe some collision on the MIs and TIs, then we will say then we will say that my distinguishing event happens. So I already mentioned in the beginning, like impossible distinguishing event. So you remember that impossible distinguishing event means we identify some event. In real world, this doesn't happen. In ideal world, it may happen. Okay. So that is what I will do here. So I will make several queries MI and obtain the responses TI. Okay. And I look for the event that there exists two different I and J such that TI plus MI equal to TJ plus MJ. That is my distinguishing event. And we know in real world, it doesn't happen. So real world probability is 0. Why the ideal world probability is at least half? Any quick argument why the ideal world probability will be at least half or close to half? Because yes, but just a very one line reason, like we choose Q equal to 2 power n by 2. So because of the Barde paradox, as mentioned, like in the Barde paradox, when you sample 2 power n by 2 random values, then you expect a collisions. Okay. So here, so 2 power n. So this is the n is this output size. So square root of this is square root of all possible output. That is 2 power n by 2. So you have to make 2 power n by 2 queries. So this is a distinguisher. You have to make sufficient number of queries. It's not just few queries at distinguisher. But you know the security strength. If n is 128, you know that up to 2 power 64 it will be good. But around 2 power 64, when you reach that junction of 2 power 64, you are not in good shape. You must be careful. So that is the security strength we can understand from this particular design, Davis-Meyer design. Okay. Okay. So there is another attack. It's called key guessing attack. That attack also has an importance in the terms of the key recovery attack. So other than distinguishing attack, how we can recover the keys. Okay. So we have several keys, K1, K2. So this is the actual key, the K. So what I am doing, I'm choosing the different multiple keys, K1, K2, KT. I'm trying to guess. I don't know the key. So K is the actual key of the construction. So this is the K. Okay. What I can observe, I know I can give MI. I will get TIs. From the MIs and TIs, I have to guess K, which is not clear, like how I can get K. So what I have to do, I have to guess the keys K. Okay. So I have a guess set K1, K2, KT. Okay. And if my guess set contains my key, suppose the key is there, then the question will be how you detect which one is that. Because there are lots of keys, so which one is mine? So I have to detect the I for which K equal to Ki. So if you look at the construction, then you know that Davis-Meyer output of the 0 will be the EK of 0, right? So if you again go back, so if you give M0, then you get Ti is nothing but the EK of MR, EK of 0, right? So Davis-Meyer output is the T will be essentially EK0, and that you can actually try to compute by using your guess key. Okay, so for every I, you check whether the TI means EK I of M. So TI represent that EKI of M. So as EKI of 0. So what you can do, you can compute the encryption of 0 by your guess key. Okay, and check whether that particular encryption of 0 matches with the Davis-Meyer output. If matches, then probably your guess is correct. But this false positive can happen. That means there can be some key K prime which is not your correct guess. Means for some I actually, what may happen that Ki is not your key, but still you get Eki of 0 or Ek prime of 0 equal to Ek of 0. So how do you eliminate this false positive? So that is one thing you have to keep in mind when you design the distinguisher. Because the false positive, we sometimes initially when you think, we ignore the false positive, but when you do the actual analysis, you have to keep the false positive in mind, and you have to refine your events a little more so that false positive can be eliminated. Okay, how we can do that? Instead of query 0 only, you can query 0 and 1, both. Okay, so now you have two things, Eki of 0, let's call it Ci, and Eki of 1, let's call Ci prime. Now both have to match. Now the false positive chance will be much less because you want two events to happen simultaneously. Okay, so in the one figure, like you have a 0 or 1, you are giving to the Davis-Meyer constructions. In case K matches with the Ki, then T0 will be the when the input is 0, T0 will be the Ci, and when the input is 1, that's T1, will be Ci prime plus 1. Okay, so you are checking these conditions for every I. So that will be your distinguishing event. The distinguishing event is now two conditions, not one condition. Just one condition, there might be several false positive. So you check two conditions, then you won't see any false positive. The false positive probability will be much less. So the distinguishing event is there exists I such that Ci equal to T0 and Ci prime plus 1 equal to T1. Okay. And then what you can calculate the analysis, like in real world, what is the chance? So is the usual steps you have to do to complete the analysis. Real world, this can happen as soon as you make a correct guess. Means your guess key is inside your, so the actual key is inside the set of your guessed key, right? That chance will be T by 2 power K or T by 2 power N if K equal to N, because there are 2 power N possible keys, okay? And actual key is one of that at random, and you are making T many guesses. So the chance of correct guess will be T by 2 power N. And as soon as your guess is correct, this event is going to happen with probability 1. Okay, so it's not exactly the 1, it's like a conditional things is coming. Like your event doesn't depend on whether the guess, you cannot detect whether your guess set contain master key or not. What you can detect whether this happens or not. To ensure this happens, your guess set must contain the master key. The probability of that is T by 2 power N. And in the ideal world, because there are two equalities, you can check that ideal world probability is T over 2 power 2n. So that if you take the difference, you can calculate that will be T over 2 power N. Okay, so T over 2 power N is negligible compared to T over 2 power N. So it will be T over 2 power N. So what you have to do, you have to make T close to 2 power N. And that is natural because you have to guess the key. So you have to guess close to the total number of keys you have. Okay. So there is a one attack where you can reduce the guess size. So instead of 2 power N, you can actually make a smaller number of. Okay, so what you can do is, so in this attack is a multi-user attack. So here you are not guessing one single key. Here you're guessing many single keys, many keys. What U represents? U represents the number of users. So suppose all of you are using the Davis-Meyer. So individually you generate your own keys, right? So you have K1, K2, KU. These are my now master keys. Okay, I want to guess those keys or one of those keys. So what I am doing, I am guessing through L1, L2, L some P. So as soon as one of my L is matching with one of your K, then I can recover that particular key by using the previous attack. Okay, so here the chance of collision, you can apply the collision, collision of two list. I have a one list of guess set, and you have a list of all the user keys. So if any one of that guess key and any one of the user key match, I can identify that particular. So it's not attacking all of you, it's only attacking one of you. Okay, but still that is vulnerable, that because why there will be attack to any one of you. Okay, but here what you if you calculate this collision probability, so you can see that the advantage will be now instead of T by 2 power N, it will be UT by 2 power N. Okay, so what UT now comes, U is the number of users, and T is the amount of guess. So this exactly coming from the collision probability of two lists, right? The one list has size U, the other list has size T. So we have this. Okay, so now say you have 2 power N by too many users, and then you can just make 2 power N by too many guess will be enough. So if you have more users, it actually is we have a multiplicative factor of reducing your guessing attempts. Okay, so nowadays the number of users is large number. So that's why it's more vulnerable. So multi-user security is actually one of the hot topics in currently, because of the number of users is increasing very much. So that's, and we have to keep this type of attack. This is the multi-user degradation. We have to keep that in mind, and how we can avoid this multi-user degradation. Those are the also important topic in the symmetric key domain. Okay. Okay, so now I will talk about the Even Mansour. This is the basic designs we use for the many. Yes. Sorry. So each user will choose their own independent keys. Like when so all users have an independent key. So independent keys. So with high probability they will have a different key. So different is not the thing we need. We need the keys are chosen uniformly and independent. Right? So they can collide. The two keys can collide, but again that will have low probability. That's about the paradox probability. If you have a 2 power n by too many users, then there will be a chance of collision of the keys. Sorry? K. Yeah. So yes, so we have to have some more things after that. Like so, I will just tell one design, like how we can do that. And towards the end of the talk, I will design one. I will touch upon one particular design. So one possibility is that you can apply some universal hash functions, okay, and then get the small output and then apply. So basically, here, so here you, instead of giving m here, so because m is large, so you can apply some kind of universal hash function before, and then you get it, and then you apply this Davis matrix. So this is one simple approach, but there are other better approach. I will talk about one of that. Okay. Yes, because we have to handle larger, what I discussed even for the next one also, like this input size will be same as like output size. That may not be useful, or in many cases, your message might be bigger. Right. Any other question? Okay. So now I will come to Even Mansour. This is very simple design, and it's also used in if you see AES. Say. If you look at the design of AES, what you will see that there is a round permutations P. So basic difference between the P and the block cipher is that P has no key. It's just a permutations. You can at home you can run the permutations for yourself by yourself, right? And the same P I am using in my algorithm. Okay, so at least some computation, whatever I am doing in my algorithm, where I have some keys in the algorithm, you can also compute some part of that. The P has no key, but there will be a key in the overall process. Otherwise, everything will be computable. So these keys will be XORed like a key additions. Like you have every key round, you have a key. Like the first round we had K1, then K2, and then you can have a successive rounds of this Even Mansours. So AES has a 10 rounds, and there are many other designs. Like mostly that if you look at any SPN designs, you will see there will be P and there will be round keys like that. So this is a very basic structure, one round of AES. Okay. So now if you look at this one round of this, how good it is. Okay. Yes. So now we will study in terms of the PRP, because it's now is my ideal object is permutations, because this is the n bit to n bit. So M is n bit, C is n bit, and it's invertible. There is no non-invertible issue. P is itself a permutation. So given C, if you know K2, you XOR, you come here, apply P inverse, you come here, XOR K1, you come here, you get here. Okay. So it's invertible. And instead of using two different keys, you can use same key, KK. You want to save the key, so you can use the same key. So single key version of the Even Mansour is this. So this is first analyzed in 1991 and was proposed in 1991, and then the analysis paper can be found in JOC 1997. Okay, so what you can do for the event Mansur, as I mentioned, the P is public. So your goal is to distinguish from the random permutations, means the or the Y will be sampled like uniformly, keeping that in mind that they are distinct, right? Uniform but distinct. This is also called without replacement sampling, also called output of the random permutations. They're all same thing. Okay, so what you are doing here, so we have event Mansur construction here. If you look at the several queries of the event Mansur, MI, which gives output CIs, so this internal value you don't know. This internal value you don't know. Okay, so you try to guess that internal value because you have the P with you. You at home you apply different XJs with the P, you get a YJs. You can compute this. Okay, so if some of the XJs, any XJ matches with any MI plus K, okay, again that may or may not happen. That we will see the list collision. Okay, we have one list of MI plus K and another list of XJ. Okay, so if this happened eventually, if accidentally, then this should happen. This because it's a I don't need a permutation because even for function, if input matches, the output matches. So we get the YJ and we get the YJ plus K, which is CI. Okay, so what I will try to identify, I will try to see that whether this thing. So if this thing happens, then what will be my distinguishing event? I mean, how we can detect? At the end, you must have an event which should be a function of your output and input. Like here, the input output are the MIs and CIs and XJs or IJs. You don't know these values. These are the internal event. Okay, so you assume suppose this happens for some I and J, then you can check that MI plus XJ is equal to CI plus YJ because they are same K. So MI plus XJ equal to CI plus YJ, which means that MI plus CI equal to XJ plus YJ. So you check that particular condition that MI plus CI equal to XJ plus YJ or not. Okay. And if this happens to eliminate the false positive things, you have to also have another event like MI plus 1. You give another input MI plus 1. Oh, sorry, this should not be CI plus 1. CI prime. So this should be CI prime. Okay, so you get a MI plus 1, you obtain CI prime. So there is no guarantee that I will get CI plus 1. So this is incorrectly written. So this is CI prime. Okay. So in the first line, like we query MI and MI plus 1, you receive CI and CI prime. Okay. And you query XJ and you receive YJ. And again, here there is a problem that you query XJ plus 1, you receive YJ prime. There is not YJ plus 1. Okay. So it will be CI prime and YJ prime. Okay. So if this equality happens, then this equality also happen. It is just simple check because you are adding 1. You are adding 1 here, adding 1 here. So this equality will also happen. So that will actually help to define the distinguishing event. So internal event is there is a collision. Okay. That can be guaranteed by QT by 2 power n. QT by 2 power n. Right. That's a least collision probability. And then you know, because this is an internal event, that's not a distinguishing event. The internal event implies that MI plus CI equal to XJ plus YJ, and MI plus CI prime will be XJ plus YJ prime. Okay. So distinguishing event is that, like whether we have these two things or not. And these two things will happen in real world. That is a least collision probability. In ideal world, because we want two things, two equalities, so we get 2 power 2n in denominator. So eventually the difference will be approximately QT by 2 power n. Okay. So what is the summary of this particular attack? Like you have to make some number of queries. So you have to observe the actual input output for one users, and you have to compute by yourself for some amount. So product of this amount should be 2 power n. Okay. So say if you have a 2 power n by too many query input output observations of real users and 2 power n by 2 computations you have done for the public permutation P, then with high probability you can guess the key. Actually, you can guess the key. So this is a distinguishing advantage. Once this happens, you know K because MI plus XJ will be the K. Okay, so this is a key guessing attack actually, but I have explained in terms of the distinguisher because whenever you guess the key, it's natural to have a key distinguishing attack. So guessing key or key recovery attack is much powerful attack than the distinguishing attack. Okay, so I skipped this. So this is one construction I want to mention. So this is XLS, which is a 3-round elastic block cipher. Ristenpat and Rogaway proposed in FSC 2007. This construction is to design the permutations, okay, but the variable length is a wide and variable length. So this is the block. You can imagine this is the block cipher. Pi1, Pi2, Pi3 is a block cipher. These are n-bit block cipher, but you see additional inputs are coming. So that additional input could be anything between 1 and n-1. So it's like expanding from n bit to n up to 2n-1 bit. Okay. So is a variable length block cipher up to 2n-1. And in the same paper, there is a method how to extend for others also. Okay. So, but that's a similar analysis can be made for the other proposal. But just to keep simple, just I want to keep this n and n plus. This can be any number of bits, but let's take n-1. So n and n-1. So 2n-1 bits. Okay. This n-1 is important because if you see how the construction works, try to understand like how. So if you have n bit, you get n bit output. Now, if you have n bit output, so then this will be n minus. So you have a q is n-1 bit. So I want to XOR the n-1 bit. So there will be 1 bit left. That is A. A is a single bit. Okay. And I get B, which is also single bit. And I parse the output into 2 parts. This is 1 bit. This is n-1 bit. And again, I XOR. I get n bit and so on. So in that way, by making 3 calls, I have a 2n-1 input and 2n-1 output. Okay. Okay. So what they have claimed, the authors claim that this is a secure, strong pseudo-random permutations, and it has been used in many designs because in the encryption algorithm, what happens like if you have a block cipher, the block cipher only can encrypt n bit, or maybe you can use multiple ways to encrypt the multiple of n bits, n, 2n, 3n. But what will happen? Your message is 2n-1 bit, or 3n-1 bits, or 3n-2 bits. You need some kind of methods to encrypt those number of bits also. So keeping that in mind, the authors propose this, like how we can handle these partial block things. Okay. And what happens if they propose they propose this and they claim that this is secure. And secure with respect to strong pseudo-random permutation. Unfortunately, it is not. Here, there is no 2.n/2 type of attacks. There is a few queries attack. Like by making few queries, you can actually distinguish. So their claim is false. So to understand that attack, I want to have a one slide presentation of the differential attack. So like you may see maybe in the next talk, or if you are familiar with the cryptanalysis for the design for the primitive point of view, like design block cipher or stem cipher, you may have seen the differential path. Like if you have a difference in inputs, then you get a difference in outputs. So we don't give a difference in one block cipher, right, or one primitive. What we give 2 inputs. So they get 2 inputs and get 2 outputs. We only note down the differences. So that's what we are doing here. Like we have a P and Q, P prime and Q prime. You get say A here is missing A, small a, X, all these things are there. And another input, you have a P prime, Q prime, A prime, like that. And we note the differences of these 2 in one slide. So delta 1, delta 2, delta 5, delta 6, all these are the differences. So delta 1 is nothing but P plus P prime. Plus means XOR. So we have difference and add is same because we are working in modulo 2 exponent operation, right? So X plus X prime will be delta 6. A plus A prime will be delta 5 and so on. Like C plus C prime will be delta 3 and so on. So by noting these differences, you don't know what PQ and P prime Q prime are, but you know the differences. But one thing you can know that if some difference is 0, say delta 3 is 0, then you know that this C and equal to C prime. Because delta 3 is 0, C equal to C prime, if you look at the next differences, delta 7 and delta star, that must be 0. Because difference 0 must go to difference 0. Because the same input, you must get same output. So that you know for sure. We will use that. Okay, so we make 2 inverse queries. So I'm first making the inverse query because it is a strong pseudo-random permutation. I can make a backward queries. So I make 2 queries, CD and CD plus 1. So there is one difference here. So in terms of the difference picture, is the delta 3 is 0, delta 4 is 1. Okay, because delta 3 is 0, I must get difference small delta star and delta 7 0. Okay, and this is delta 4 is 1. So all the linear operations you can work in the differential numbers, like whatever difference number, because this difference is the linear function. But whenever you have a pi 1, pi 2, then you cannot preserve this difference pattern. Okay, so we have a delta 7 0, delta 4 1, that this difference will be 1. That's okay. Okay, so this difference is 1, and this difference must be 1, right? So this difference must be 1. So delta 5 should be 1, because I gave delta 4 1. So delta 5 is 1. That's the first observations we made. And delta 6 can be anything. I don't know. And small delta can be either 0 or 1, because I cannot control. But this can happen with probability half. So with probability half, the small delta can be 0. So let us assume that small delta, accidentally it happens 0 with probability half. Okay. So in this case, so what we have, like we have small delta is 0, capital delta 5 is 1. Okay. And we know P and P prime, because that is what we observe after making the backward query. So what we have, that pi 1p plus pi 1p prime, the difference of these two will be 0 is the first bit and 1 is the n-1 bit. Actually 0 power n-2 1 1. Okay. So this is what you know. So that's what I mentioned in the next slide. Now I make 2 more queries. So we're not done yet. So just 4 queries. So 2 backward queries and then 2 forward queries, then we will be done. So we know that pi 1p plus pi 1p prime is 0 and 1. So pi 1p and pi 1p prime will be again the same thing, a and a, 0 and 1. Okay, but I choose a different q star and q star plus 1. So just I make a difference 1, so that after you XOR, the difference will be 0. So delta 6 I force to be 0. Delta equal to 0, again, like with probability half, I already know that this will be 0 with probability half. Okay, so once delta 6 is 0, the output difference will be 0, and this 0 will come here. So that's what you observe, the D star, I don't care this output. These two output must be equal. That is to n-1 bit output, to n-1 bit output should be equal. In ideal world, this can happen with probability 1 over 2 power n-1, which is very small. Okay, so this is what we will check, whether the D star, this double star, I mean that actual, whatever you observe, in ideal world, it may not be same, but in real world, it has to be D star. Okay, that's my distinguishing event. So in real world, the distinguishing event probability is half, because I depend on this small delta happen to be 0. Okay, that's why I need the half. And ideal world, the probability is 1 over 2 power n-1, because these are n-1 bit equalities. Okay, so now the difference is close to half. So this is the attack. Is an Indocrypt 2015, I think, or I forgot the year. So this is the attack by me, myself only. So I found this attack for the SPRP for the XLS, which was not second. After that, the authors retract the paper, but in the print, so you can see the note by authors in the XLS. Okay, so there will be so this is the last part of the talk. So I have 20 minutes left. This is a composition of primitives. So this is also recent work of myself, published in Indocrypt 2020. So you see, like you have I've already discussed like the compositions of the round permutations, right? So we have several permutations we compose, or several functions we compose. Okay, that's what we do for AES. For permutation is okay, you can do, but for functions you should not do. That's what you have to keep in mind, because if you use more rounds, then the security will be less. Okay, but there will be mathematical way to guarantee like why it is so, and given a design, it may not be apparent that whether it's a composition or not, but after looking at the design a little bit, you may identify some composition nature. So understanding composition is important. Okay, so what you're composing several primitives, P1, P2, PR, say R types. So forget about the general R, so just focus R equal to 2. So you can do it for general composition for R many, but just for understanding that take R equal to 2. Okay, so you have a 2, P1 and P2, and you get out. Now, what are the possible choices of P1 and P2? Okay, P1 can be function or permutation, right? This is the one possible choices. And another vertical choice is this could be public or secret. What do you mean by public and secret? Okay, if you take permutation, then secret means the block cipher. The secret permutation is the block cipher. And if you take a public permutation, as I mentioned for the event Mansur, or look at the AES sound permutations. Okay, so those are like if you know the SHA-3 hash function, the K-chuck, there is a permutation inside that hash function. So there are several permutations available in that where there is no. Okay, so this is the ideal. You could consider that as the ideal permutation, and we can do the same thing for the function also. You can have ideal functions and the secret functions. Secret key functions, maybe you can consider Davis-Mayer here. Davis-Mayer is not ideally secure, but is secure up to 2.n/2, right? So so we can have a secret random function or secret random permutation. We can have a public random function, public random permutation. So there are 4 possible choices. So P1 and P2 would be any one of these 4 choices. So gamma represents the function, pi represents the permutation, and sec represents the secret, and pub represents the public. Okay. So there are 4 choices, and you can take any 4 here and any 4 here, 16 combinations, and you want to analyze that. You can clearly see some choices are meaningless. Which choices are meaningless? So you can take 16 choices, 4 choices of here, 4 choices here. There might be some compositions which are not meaningful. We are analyzing the distinguishing security. We want to have a PRF or PRP security. Which choices will be meaningless? At least one must be secret. If I take both public, then it's again a public function. So we are not going to analyze the public function. We're going to analyze some secret thing. So that there should be at least one should be secret. Okay, so that keeping in mind, you try to explore the different possibilities. Okay, so the first question, basically, this is the question we will ask here: is the composition is Bardebound secure or not? Actually, it will be Bardebound secure. And with Bardebound secure means 2.n/2, whether it's a beyond Bardebound or not. So that is what we demand, because if n is small, n is 128, n/2 is 64, 2^64, we may not be happy. Nowadays, our infrastructure is better and better, so we cannot bet on 2^64. Maybe we want to increase the security beyond Bardebound. That's called beyond Bardebound. So that's another direction of the research in symmetric key, how to design something which is beyond Bardebound secure. So one way you can do that, okay, you rely on Bardebound secure, increase your n. Why 128? Make your n 256 or make your n 1000. Okay, that's okay. The other way, okay, you keep your n 128 because we have AES 128. We don't have AES 1000. So why not you have a AES 128? Use some designs which has beyond Bardebound security. Okay, so what are the things you can easily observe that if you have a random function, secret function, and then if you compose with any permutations, it must be random function. Because random function followed by any permutations should be a random function. So this is the intuitively you can see, but if you want more concrete analysis, you can actually check. And same thing in the other way, like if you take any permutation followed by a random function, secret random function will be a random function. So these are the simple compositions that we can first check. Okay, so the compositions that might be interesting is if you have a random functions, you compose iteratively, say twice or 8 times. Okay, so then it is not a perfectly random function. It has a security up to Bardebound. Because if you see in this diagram, like if you take 2 different input x and x prime, then there is a chance of collision. Okay, so if there is a collision, then you get a collision here. So collision preserves. Collision will be preserved in the final outcome. But if there is no internal collision, still there can be a collision. Because gamma is a random function, either public or secret. Okay. At least one of them is secret, but I don't care. I don't care whether public or secret. Okay. So then also, so basically you have a twice chance of having collision in the real life, in the real world. In the ideal world, you will have a half chance of that. So basically, the real world the collision probability will be twice of the ideal world collision probability. Now, if you take a difference, you get 2 minus 1 will be 1, like q² by 2 power n. That will be your advantage. So to make the q² over 2 power n significant, you have to go up to 2.5. Okay. So same thing you can do for R many rounds. So if you have R many rounds, then you can actually apply R many iterations. So in Indocrypt 2017, we have shown that the security can maximum achieve RQ square by 2 power n, but you can actually prove the other direction also, that this you can have a distinguishers where the advantage is this, because the collision probability will be your distinguishing event. Yes, collision event will be a distinguishing event. As soon as you observe the collision here, then you return 1, otherwise 0. And what is the chance of having collision, or when this collision can happen? If it collides here, then the collision will preserve till end. If it doesn't collide here, then it will collide here possibly, then it will continue with the collision, and so on, right? So all these events are disjoint event. Okay, so the collision probability will be order of RQ square over 2 power n. Okay. Okay, and that's the thing here. Like someone has asked, like what we will do when we have a bigger message. So okay, there is something called EWCDM proposed by Pagliatti and Ian in Crypto 2016, and in next year in 2017 there is a dual version of EWCDM. Okay, by many kettle. So, but there is something happened. I am going to tell that. Like, so what is this dual version? Okay, we have a pi1 output, and then you take the hash out, XOR the hash output, and then you apply this known picture. It's called Davis-Mayer, right? We have already seen the Davis-Mayer. This is the Davis-Mayer. So all block ciphers, right? So this message can be large. This is again part of the message, but you can consider that as a nonce, maybe something which doesn't repeat. Okay, so this overall picture is your new pseudo-random function, and initially in the paper Crypto 2017, authors claim that it has a beyond the bound security. I observed that it is not. Okay, the reason is simple, because if you look at the same design into closely, you see that two part. One part is this one. That's you can. All these are secret. So this is a secret random function looking things, and there is another secret random function looking thing. That's a Davis-Mayer. So it's basically composition of two secret random function. So it cannot give more than the bound security. So the claim was beyond the bound claim was wrong. So I reported that, and the authors get time to retract the particular claim from the crypto proceedings. So initially it was there, but later on they have removed the particular claim. Okay, so this is what happened for the EWCDMD. And then I look at the final one, the last one for today. So that's when you have a so there are two. Okay, so this we can ignore. So this is okay. So this composition. So that is another interesting one, the final one. So we have now I'm studying the random function, but one of them is public S, or one of them is permutations. Okay, not both are function. We have already seen if both are function, then you know that it is Bardhavan secure. What will happen if one of them is permutation? If you take one permutation and one function, then is it about the beyond Bardhavan secure? It is no, if you have a public random function. So if you have a like this, so first take this composition rule 1. So if you take this particular construction, that's easy to see why it is not beyond the bound secure, or why it is what is the distinguishing attack, the bound distinguishing attack for this particular composition. So because it's public, you look for some x and x prime such that it's a collision of gamma pub. So gamma pub of x equal to gamma pub x prime, and that collision will remain. So you just after you find this collision, that you can do offline. Once you have x and x prime, you give that x and x prime, just two queries actually in the online. You get y value should be same in the real world. Okay, so that will be a distinguishing event. So is the number of queries is 2, but you have to make offline queries to get a collision. That's the 2 power n by 2. The most interesting one is the other one. When you have a gamma pub inside, the internal one. Now it cannot compute the collision here, because you can compute collision, definitely. You can look for the collision on the gamma pub. but you don't know that those collision will be eventually the part of the construction output. Like, because this input of the gamma pop in the construction is the output of the PISEC that you don't know, right? So how we can attack this particular composition? Okay. So here, again, we will do at offline, like we'll consider different Xi's and you get different Yi's. Okay, so we compute this gamma pop in offline ways. And we make a queries, say some J's, a distinct queries. Doesn't matter what is the input here, distinct queries, you receive CJ as output. So what you observe that if Xi equal to ZJ, so ZJ is the internal value that you don't know. Okay, so that's the internal event you are hoping for. So if this internal event happens at Xi equal to ZJ, then you know that Yi equal to CJ. Right? Because it's the same function, gamma pop, public function. So you know that Yi equal to CJ. If this equality doesn't happen, then also Yi equal to CJ can happen. Because it's again a function. The collision can happen. Okay. So what you are doing here, now you're making the offline queries Xi's to get the output of Yi's. Okay. You make the online queries, the construction query, on the F is the total functions. You get the output CI's or CJ's. Okay. And you see whether there exists any I and J, whether Yi equal to CJ. Just you look for the least collision, whether there is a collision between between Y values and C values. Once you find such, you say 1, otherwise 0. So the analysis is, as I mentioned, like if Xi is equal to ZJ, then we know that Y equal to CJ. And if Xi is, they do not match, still you have a higher chance of having the equality. Sorry, if they do not match, then still have a collision probability. So it's like a double up for the ideal case collision probability. So you have to do a little more analysis on that because you need to lower bound the advantage. So basically, you have two probabilities. You have to lower bound the advantage. Whenever you want to lower bound the difference of two probability values, you have to lower bound one particular value and upper bound other particular value. So you have to be more careful on the analysis part, but you can do that and you can see that it's actually order of like P times Q by 2 power n. The advantage will be like least collision probability. And you can apply that for the SOKSE21, which is published in Chen et al. Published by Chen et al. In Crypto 2019. So in the paper, they proposed this design and the authors claim that it is beyond Bardhaman secure because we need more security. So this is the construction they claim. Now you see this here, the pi 1, pi 2 are public. Is like a replacement of Ibn Mansur, or it's like a combination of Ibn Mansur and Davis-Meyer, right? But all these public permutations, we have a K secret there. You can imagine like this is like same construction can be viewed like, okay, we have a Ibn Mansur, that's my secret things, and we have a Davis-Meyer, but the public one. So it's the composition of secret and public. So exactly false in the category I have discussed. So it has a 2.2 query attack. But the author claims beyond Bardhaman security. Okay, so that's a false claim. So that's a wrong claim. So we have I have shown in Indocrypt 2020, basically in the same paper. Sorry, in the same paper, I discussed that attack. But to motivate this attack, I considered the compositions of the different primitives. And as a particular case, like we have the attack on SOKSE21 and also the attack on the dual version of the EWCDM. For the composition of two functions. Okay, and that's all for this talk. So what we have analyzed, like we consider the Bardhaman security of Davis-Meyer's Ibn Mansur 1 round. There are some other results on the Ibn Mansur multiple rounds, the key alternating ciphers with the multiple rounds, and those are more difficult results. For our rounds, what is the security? And there are different variants depending on reusing keys and reusing the permutations. But the security of some generic compositions. That's the second part of the last part of the talk. And as in applications, we see the Bardhaman attack on the dual version of the EWCDM and the SOKSE2. And we also have seen that XLS is not secure. It's not a Bardhaman point of view. It's not secure. You have a 3 or 4 query attacks. So what are the possible things you can look into these directions? Okay, in terms of this, the XLS point of view, So I have a follow-up work in the essay script next year. Like XLS is not secure. Okay, so what happens? Like is it? Can you modify the XLS and make it secure? Okay, so what we have seen that if you make 3 calls, it cannot get security. These are well-known results. We knew much before that 3-round Dubidakov is not strong pseudo-random permutation. 4-round Dubidakov is strong pseudo-random function. So 4 call at least required. And I proved formally that 4 calls is at least required. So 3 calls is actually is not possible. So if you modify the XLS in little slightly variant, it won't be secure. You have to have 1 extra call. Okay, so XLS cannot be repaired. But what happens, like the minimum number of blocks have a calls for other type of designs where there are 2 ways to extend the attack, extend the minimality requirement, like how many calls you must need to achieve something. Okay, so this is not a proof paper. That will be an attack paper, because if you use 1 less number of calls, how we can attack? That's what we have to show, and that you can. You have different views, like what you are demanding, like whether you want to achieve pseudo-random permutations or strong pseudo-random permutation, or whether you want to achieve beyond but the bound or not. What is the so in the so we have a 3-round call, we have a not secure. 4-round call, we have but the bound attack. Or if you know Dubidakov, 4-round Dubidakov is but the bound secure, and there is a matching but the bound attack. But can we have a 4-round beyond but the bound construction? Or can you prove that now 5-round is minimum requirement to get a beyond but the bound? So the 2 aspects. The another aspect is the studying the minimum call in terms of the security level. And there are another important question in the paper. There are several variants of the SOKC2 in the same paper where there is a flaw in the design or the proof. But there are other variants. But the author claims that's not secure in the but the there is an attack in the but the bound, which is not apparently is not again correct. So all those variants we can study, the other variants we can study. What is the exact nature? Whether it's but the bound secure or beyond but the bound secure, those other variants also not known. Even if there are some claims, but those claims are also not correct. So if you can look into that paper, the Kipton 2009 paper, SOKC2 was done, but like we know, it's a but the bound secure. We have a but the bound attack. But what about the other variants? Like variants are mostly due to like choice of keys and choice of permutations, and just you instead of XORing this by that, you XOR that by this. Like you just play with this design. So if you go to the paper, you see the variant which are very close and try to analyze those variants. So these will be the other important directions for that particular paper in mind, because this is published in Crypto 2019. I have studied that a little bit, but after that I didn't get time to go study further on that. So if you are interested, you can further explore this particular paper. Okay, thank you for listening this lengthy talk. Maybe any question?
Yeah, question. Any comments?
So anyone from online can also ask question. Otherwise, we will take a break.
Okay.
Yeah.
Secret followed by a public one. So that's kind of a but the bound secure. But what happens if I just introduce another secret component? So secret, public, secret.
Oh, okay. So this type of composition I have not studied. Or for 3, it will be more complex. Yeah.
Because that kind of thing, because you cannot have.
Yeah, so if the designs which uses more calls, like 3 calls or more calls, then you can fit into that category, right? So it will be more complex. So I have not thought, and I have not seen.
There are not such designs.
Yeah, so if we have some designs already which can be fit under this 3 compositions, then we could have studied that. But so basically my motivation was to study SOKC2 and the EWCDM. Those are fit in under composition of two primitives. That's why I decided.
Okay, so let us thank again our speaker. And let us take 5 minutes break and we will start again 3:35. So only 5 minutes, so don't go outside.
তাহলে এটা নিয়ে মাছ ধরার করতে গেলি হ্যাঁ অ্যাকচুয়ালি এই ক্যামেরাতে না পুরো স্ক্রিনটার কিচ্ছু দেখা যাচ্ছে না, পুরো জ্বলে যাচ্ছে। মানে তুমি দেখলে এটা বুঝতে পারছো, এই যে দেখবে আসো উপরে একটু বুঝতে পারবে এইটা জ্বালা থাকলে বলছি পেছনে স্ক্রিনটা পুরো জ্বলে যাচ্ছে না স্ক্রিনটা। হ্যাঁ
Is it working? So thank you for this opportunity to. I'm glad to give a talk at Indocrypt this year. So my talk will be about tools and algorithms for cryptanalysis. And sorry, I just landed this morning, so I'm a bit tired. I hope this will be good enough. So today I will talk about tools and algorithms for cryptanalysis. And in the case of symmetric key cryptography. So basically, in symmetric key cryptography, Alice and Bob want to share a secret to exchange some information between them, and they share a secret, a common secret. So we have many symmetric key primitives. For instance, block ciphers, stream ciphers, hash functions, MAC, and authenticated encryption. And the goal is to study the resistance of those primitives. More formally, a block cipher is a function. This one. Okay. A function of this type. So it takes as input a key K of K bits and a plain text of N bits, and it outputs a ciphertext of N bits as well. Okay. And we say that a block cipher is secure if there is no way to distinguish it from a random permutation. Okay. And the goal of cryptanalysis is to recover the secret key, or at least to highlight some unexpected behaviors of the target, of the primitives under target. Okay. Of course, we have some constraints because the security of a block cipher of any symmetric key primitive is a computational security. And so we have some constraints. So first, the time complexity should be less than a loop over all the possible keys. And the data complexity in practice should be less than the whole codebook. Okay, because if we have access to the whole codebook, there is no need to retrieve the key. But sometimes you may find some attacks with the whole codebook. It's still interesting to understand the security of the primitive. And of course, there are many adversarial models, okay, depending on the strengths of the adversary. So in the case where the adversary is the weakest, it only has access to non-plain text. Okay, so he knows some pairs of plain text ciphertext, but he cannot choose them. And then we have much stronger models. We assume a much stronger adversary. So for instance, we assume he can choose the plain text for which he can have the corresponding ciphertext. And we can also assume that he can choose them as a response of the previous computations he just made. We can assume he can also choose for the ciphertext he wants to have the corresponding plain text. And we can also consider very strong adversary, like for instance, in the related keys model. So here the adversary is able to encrypt some data under some secret but related keys or related subkeys. And then we can also go further by looking at the side channels attacks, fault injections. Okay. So when no attack is found on a given cipher, we need to look how it is constructed, and we still want to give some information of this about this cipher. Okay, and most of the ciphers block ciphers are constructed this way. So basically, a very simple run function, which is iterated many times. Okay, and typically, if we cannot attack the whole version of the cipher, we will look at the resistance of the run reduced versions and look at the maximum number of runs we can break for a cipher. And if we cannot break anything, or we can also look at the security of internal components. So for instance, the security of S boxes or linear layer, or many things for the of the permutations, for instance, if you study hash functions. Okay, so this might seem a bit artificial, but actually it's very important, because over the time attacks only get better, and better be safe than sorry. So we have access to many different type of cryptanalysis techniques. So here you have some known ones. So for instance, differential cryptanalysis, linear cryptanalysis, integral distinguishers, invariant attacks, meet in the middle attacks, algebraic attacks. And the goal, our goal, is to find which technique we will apply against a given target, and how to apply the technique in the best possible ways. Okay, because there are most often many possible ways to apply the attack, many parameters for those attacks, and the goal is to find which will be the best parameters. So for instance, here you have an example of a Demirci-Selçuk attack. So I will not really explain this attack in practice, but what is important here, so basically this is a representation of AES, and the relation between the state Z5 and X6 here is the multiplication by the mixed column matrix of AES. So just by an MDS matrix. And here it's there is an equation between the 4 bytes which are blue there, and the byte here which is red, because there is an equation between those 5 bytes. And if we consider all the possible variants of this attack, we can choose any configuration of 5 between the 8 bytes of one column. Okay, so 4 bytes here, 4 bytes here, and we choose 5 of them. And this gives a variant of the original attack of Demirci and Selçuk. And we can do exactly the same at the input of this attack, which is something about differential, but it's not really important here. But what is important is that we can also consider all the possible choices. We select 5 bytes that will be active in one column, and we obtain another configuration for this particular attack. And so if we look at all the possibilities for this attack, we have almost 2 to the 16 possible configurations, okay, for the Demirci-Selçuk attack against this Round-reduced variant of AES. And you see that it is impossible to exhaust all of them manually. Okay, 2 to the 16 is like 65,000. And we need to use tools and algorithms, so the computer, to exhaust all of them and find the best possible configurations. Okay, that's the introduction. So when you want to search for the best possible attacks or the best possible distinguishers, you will face 3 main problems. First, the search space can be very large. Here, for instance, 2 to the 16 is not, it's large for a human, but it's not very large for a computer. But on some problem, the search space is very, very large, like 2 to the 100 or 2 to the 1000, I don't know. So it is completely impossible to exhaust. And so we have to find like small enough subspaces, which we are sure will contain at least one optimal solution, or something that should be very close to the optimal solution. The second problem is that computing the complexity of an attack can be very hard itself. Okay, for instance, computing the complexity of a boomerang attack, or many, I don't know, even for Demirci-Selçuk attack, you need to compute the entropy of some round key bytes. And because the key schedule of AES is non-linear, computing the entropy of those k bytes is not an easy task. Okay, so this is most often this is very complicated, and it includes rank problems because we need to optimize the intersection, the dimension of some of the intersection of some subspaces. Okay, and we also need to find which tools or which algorithm we will use. So will we develop an ad hoc algorithm to solve the problem we want to solve, or we will use like generic solvers like CP, SAT, or MILP solvers? Okay, so this is not clear which tools or which algorithm we have to use. Okay. And I will try to in the following, I will try to give you some examples for each of those points. So first, let's start with the search space. An important cryptanalysis technique is differential cryptanalysis, okay, in which what we want to do is to know whether there exist pairs of input and output differences which occurs much often than for a random permutation. Okay, so here you have the cipher under study, okay, which is E0 combined with E1, and you add some difference delta 0 at the input, and you observe some difference delta 2 at the output. And you want to know if there is a pair delta 0, delta 2, which occurs much more often than the other pairs, for instance. Okay, because for a random permutation, it should all pairs should have the same probability to occur. And so if one pair occurs with an unexpected high probability, then you have a distinguisher against the permutation, against the cipher. The problem is that it's too complicated to search for all pairs. And so another idea is to split the cipher into smaller and simpler functions. So here into E0 and E1, and to search for a sequence of differences. Okay, so basically this is what we call a differential characteristic, because we will force the difference after each operations involved in the cipher. Okay, so it simplifies. It seems it simplifies a bit the problems, but in practice, not. This is still very hard. Okay, you cannot try every possible delta 0 because there are too many of them. Typically, there are 2 to the 128 possibilities for delta 0, so you cannot exhaust all of them and search for all the possible differential characteristics to find the ones that will occur the most often. Okay, so this is still hard. To simplify this problem, we can look at truncated differential characteristics. So this time, instead of searching for the values of the differences, we will only search for the truncated differential characteristics. So basically, for each byte, we will say whether it is active or inactive. So whether there is a difference, a non-zero difference on this byte, or if the difference on this byte is 0. Okay, so now the problem is much easier. Okay, because for instance here it's the round function of the block cipher skinny, and here the input is a 4x4 matrix of bytes or of nibbles. So if we want to exhaust all the possible differences here, you have 2 to the 128 or 2 to the 64 possibilities. But if you want to exhaust all the possible truncated differences here, you only have 2 to the 16 possibilities. Okay, because for each cell, you have only 2 choices. Either the difference is 0 or it is non-zero. Okay, so it simplifies a lot. And we can study truncated differential characteristics. And this is related to differential characteristics because if we know the number of active S boxes, we have a bound on the probability of the corresponding differential characteristic. Okay, because all of that are linear operations, so we don't really care. And here, what is important is the probability of the transition from here to here, so through the S box. And so, with by studying truncated differential characteristics, we obtain some bound for the resistance of the primitive against differential cryptanalysis. Okay, but it's not that easy. Okay, studying differential characteristics, truncated differential characteristics is not an easy problem because when you XOR two active differences, there are two possible choices. Either the difference is 0 or the difference can be non-zero. Okay, so you have two choices. And okay, so there are many possibilities, many trails to try for. And the goal is to find the ones minimizing the number of active S boxes. So to solve this problem, we can do dynamic programming. It's very simple. So basically, we use the fact that to compute what happens after R round, we only need to know what happened after R-1 round, and to compute the possibilities after one more round. Okay, so basically you start by a tab, okay, C, which for each round and each possible state contain the number of active S boxes, the minimal number of active S boxes required to reach this state after R round. And you can update it this way. So basically you will first set that you need an infinity number of active S boxes to reach it. So it's just an initialization. Then you, for all states, you compute all state S prime. Okay, so basically you start from S prime, and you want to reach S, and you have computed all the possible state S primes that can reach S through one round of the function, and you update now the array. So basically you look at the number of the minimum number of active S boxes to reach S after R-1 round. You add the number of active cells in S prime, and you give a new number C. And if C is lower than the number already stored in C or S prime, then you update it. Okay, and it's very simple. It's only use the fact that what happened 2 rounds before cannot affect what will happen some rounds after. Okay, rounds are separated, and the only thing that is important, that matters, is the number of the states you start from, and the number of active S boxes required. You will have to activate to reach it. Okay, and so for instance, on Skinny, it's just R-1, so the number of rounds, so this loop, and times 2 to the 20. So basically here you have a loop on 2 to the 16, and for each state there are on average 2 to the 4 state S prime. Okay, so it's very easy and takes 1 second on a simple laptop. But that was in the case where there are no differences in the key. And for instance, in Skinny, you may have 3 keys. So basically 48 cells of key. And if you want to add differences in the key. The problem is that the complexity of dynamic programming becomes very, very large, okay? Because you now your state, so you can still do dynamic programming in theory. But the problem is that one state is composed by the state, the internal state, and the key. And so basically you have 2 to the 64 possibilities. Okay. Using some trick, it can be reduced to 2 to the 48, but still you cannot store, you cannot have arrays of size 2 to the 48. It's too big. Okay, we can perform 2 to the 48 simple computation. It's doable, but storing as many I don't know bytes, it's impossible. At least it will not be fast. Okay, because 2 to the 48 bytes is like I don't know 256 terabytes, and you don't have enough RAM to store it, so it will be slow. So what you can do to overcome this issue is to be a bit more clever, and basically we can use the idea that the best truncated differential characteristic will involve very few active bytes in the key. Okay. And so most of the configurations with active bytes in the keys are actually not really interesting, and will not lead to good truncated differential characteristics, so you don't have to look at them. And what we used, what we proposed for as an idea, so basically in Skinny, the key at each round is applied only on half of the states, and it is only a permutation for the key. The key is the key schedule is only a permutation, basically. Okay, so if this byte is active at this round, then another byte will be active at the next round, at the next 2 rounds. Okay, and what we propose is to run like a degraded search, and if we didn't choose whether the key bytes are active or not, we set them to 0, and we allow here 0, 1 as output of the S box. And so basically we will search, we will run a search assuming that everything can happen in the best possible scenario for the key bytes for which we didn't set whether they are active or inactive. And because half of the states does not depend on the key, we still get some interesting bounds, and we can cut some of the branches, some of our tree search. Okay, basically we will see if we see that okay, if this one is active, this one is active, this one is active, this one is inactive, this one is inactive, we see that we cannot reach independently of what happens in the other key bytes. If we cannot reach a truncated differential with better than what we already found, then we know we don't have to look at the possible values for the other ones. And so that's the idea we used to solve this problem on Skin. And so basically, it's still dynamic programming, but you have to do it in a clever way to remove all of the uninteresting cases, which are too big to store. Okay. And actually, we did that because at the beginning, we wanted to compare different methods to retrieve the best truncated differential characteristics against the skinny block cipher. And so we tried as well all generic solvers. So we tried to modelize this problem with for MILP, for SAT, and for SHOCOS or CP programming. And I think it's interesting because, so we see for, in the single key model, so dynamic programming is very, very fast. Okay, it's only 1 second, and the number of rounds does not increase it here. While, for instance, for MILP, it's quite huge. For instance, for 20 rounds, it's 16 hours. And for instance, Shoko, it was unable to obtain any result after 24 hours of computation for 16 rounds. But if you look at the TK3 model, so the models for which for us it was most complicated, okay, because there are a lot of keys, and so it was very complicated to search for the best truncated differential characteristics with our technique. So, for instance, in TK3, after for 30 rounds, it requires like 500 gigabytes of RAM. So it's quite a huge computation. Then you can compare for MILP, and we reach approximately the same time as MILP. Okay. So here there is always 20 seconds of initialization of stuff in our tool, but if you subtract 22 seconds, we get approximately the same times. Okay, so that's very funny. And you look at the MILP modelization, more there are degree of freedoms for the key, more it is easier for the MILP solver to get the solution, the best solution, in a small amount of time. Okay, so I think this is very fun. And I don't have a real explanation for that. Okay. Here, I think it is very slow for SK because all rounds are separated, and I think he performs very bad choices at some moments on the variable on which it branches. But I don't really, I don't know how to explain why it is much faster in the TK3 model than in the TK1 model. I think this is because there are more degree of freedom, and it seems easier for MILP to solve it. But then you can look at SAT and CP, and they are completely okay. They cannot output any interesting result in less than 24 hours. So I will explain a bit more about MILP and what is it, and how to use it to modelize cryptographic problem. So basically, MILP and an MILP model means that you will describe your problem using only linear inequalities involving some variables, and those variables are typically integer, and more precisely for cryptographic related problems, they are binary variables. Okay, so it looks like this. And so sometimes you want to optimize some quantity, maybe like minimizing some sum or maximizing it. But sometimes you just want to know whether there is a solution or not. This is, for instance, the case if you look at division property and stuff like this. And so how it works internally. So you have your problems. We have some algorithm to find solutions of these problems if we remove the constraints regarding the integer characteristics of variables. So basically, we will search for a real solution, a continuous solution, and so we can obtain a solution of this problem. So if it does not have a real solution, it will not have an integer solution. So you can stop the computation here. And if it has a real solution, and if all variables are not integer, you can take one, which is fractional. So for instance, here they take v equals to 3.5. And then you will split the model into two parts. One for which you will add the constraints v is smaller than 3, and another one for which you will add the constraints v is greater than 4. Okay. So basically, you removed the fractional solution you just found, and you separated the model into two parts that should be easier to solve. And so on until you get solutions that are either infeasible or that are completely integer. Okay, all the variables are integers, and so you get the bound. Okay, so that's how it works internally. So now I will show you how we can modelize the search of truncated differential characteristics on on AES. It will be simpler, and it's more interesting. So AES, I remind, there are 4 simple operations. So first, the add run key. So the key is XORed to the internal state, bit per bit. Then the same S-box is applied to each of the 16 bytes. Then the rows are shifted. So that's the shift rows operation here. And finally, each column are multiplied by the same MDS matrix M. Okay. And there is no mixed column for the last one, but it's not really interesting for example. And that's the key schedule of AES. So AES was standardized in 3 different versions: 128, 192, and 256 bits of keys. And that's the different versions. So basically, it's only XORs. And the last column goes through the S-box. And for the 256-bit versions, the middle one also goes to through the S-box. So how we can create MILP model to search for truncated differential characteristic against AES. So for the S-box operation, it's very easy because if the input is active, the output will be active and vice versa. Okay, so the constraint is only an equality here for this operation. For the shift row, it's exactly the same. It's only a permutation. So the shift rows operation does not modify the activity of 1 byte. Okay, it's just a permutation. So still another equality constraint. Now for the mixed column, we know that the matrix used in the mixed column is MDS. And so we know that we have this. So basically, if so either both columns are inactive, so we have only zeros here. And if 1 byte is active, we know that at least 5 have to be active as well. Okay. And for each configuration, we know it is a valid configuration. So this can be written by these inequalities. Okay, so for now it's not really an equality, but this is a constraint we would like to implement in MILP. So we want that the sum in 1 column is either equals to 0 or greater than 5. So, okay. And to implement it in MILP, we will introduce an extra binary variable E and write those 2 constraints here. Because if E is equals to 1, we impose that this is greater than 5 and this lower than 8, which is always true. And if E is equals to 0, so this is 0, and this is always true. But we also impose that the sum is lower than 0, so it will be equals to 0. And this is how we can implement with 2 inequalities and 1 extra binary variable this kind of constraint. And it works for a lot of similar constraints. So this is a classical technique. And now for the key, so we have 2 cases. If there is no difference in the key, it's just an equality. Otherwise, we have a XOR with the key, and we just want that the sum of the 3, so this one, and the corresponding byte on the key, should be different to 1, okay? Because it is not possible that only 1 is active. And this can be described using 3 inequalities. And more generally, if we have an equation like this with n variables, we will need n inequalities. Okay, so we have 2 versions depending on whether we will authorize difference on the key or not. So the question is the model I just presented is correct? So the answer is yes. If there is no difference in the key, all the solution of the MILP model I just created will be correct in the sense that for all of them, I can find S boxes. So I can choose all S boxes so that I have a valid instantiation of these truncated differential characteristics. I can find a valid differential characteristic associated to this truncated differential characteristic. But now, if I consider differences in the key, the model is not valid in the sense that many truncated differential characteristics we will output are not possible, does not satisfy linear relations of the AES equations. Okay, because there are some things that happen which are not captured by the model we just wrote. So, for example, we have here okay, a truncated differential characteristics, which is valid according to our model, but in practice, it will never be instantiated because it does not satisfy this relation. Okay, this is a linear relation. The mixed column is a linear operation, so I should have this equation should hold, but here it does not. Why? Because actually, so this column here in the key is equals to this column here in the key. Okay, because by the key schedule equations, this column, the difference in this column is equals to the difference in this column, so 0, plus the difference in this column. Okay, so they are both equals. And now if you look at what happened in the internal state, it means that this column here is equals to this one. Okay, because we just have a XOR and this one is 0. So this column is equals to this one. And similarly, those 3 bytes here are equals to those 3 bytes here. And in practice, it is not possible that we have those equations, okay? Because here it means that we should find 1 byte, so that's the difference when we apply the inverse of the mixed column, we get 0, 0, 0, and 1 active here. And here, another byte, and when we apply the mixed column minus 1, we obtain 0, 0, 0, and it's not possible. Okay, so this model is not correct in this case. So how to solve this issue? The problem is that our model does not capture all the linear combinations we can do between the equations describing AES. So the first solution will be to compute all the possible linear combinations between all equations involved in the AES equations. But in this case, we will obtain too many constraints, and the model will be very slow to solve. Okay, so this is not how we should do it. Another possibility is to use a callback. So basically, you keep your simple model, and each time you find a solution, you just perform some linear algebra, check whether the solution is valid or not, and if it is not valid, you will add another constraint to the solver, okay, to reject the solution. And actually, for some problems, it will be fast, but it depends if we need to add many constraints or not before finding the optimal solution. And for AES, it is not necessarily the case. We might have a lot of constraints to add before we obtain the optimal solution. And so as open problem, I don't have a solutions to propose to you, but as an open problem, it will be interesting to find how we can find this issue. If can we find a trade-off between both approaches, and in which case, so I think there are some linear combinations of the original system that are very important to add to the model to simplify it. And okay, so it's something you can think about, and I think it's very interesting. Now I will continue on differential cryptanalysis, and I will talk about something a bit more sophisticated than only truncated differential characteristics. I will talk about boomerang distinguishers or boomerang attacks. So basically in a boomerang, what you want to do is like you add a difference at the input. You obtain some ciphertext, a pair of ciphertexts, and you add the same differences on both of them. And now you decrypt the corresponding ciphertext. And the question is whether the difference between the new plain text is the same as the one we used at the beginning. Okay, so the idea is that combining two short differentials can be much better than using a long differential. Okay. The problem is that to compute the probability of a boomerang, we used to assume independence to evaluate the probability. Okay, because here I used a differential here and a differential here. Okay, but in practice, this assumption of independence does not hold. Okay, there are many problems at the junction of both trails, and we have many examples of non-returning boomerangs or of boomerangs that returns with a much better probability than expected. Okay, and in 2018, Sid and its co-author introduced the boomerang connectivity table to unify the previous works, and which is actually only a pre-computation of all boomerangs through one S-box. Okay, so you have the formula here. And this is very interesting because now assume we want to search for the optimal boomerang distinguisher. When we assumed that the two trails were independent, it was enough to search for the best differential characteristics on R1 rounds, which has some probability P, to search for the best differential characteristics on R2 rounds, which has some probability Q. And we knew that by combining them, we will obtain a boomerang characteristic on R1 plus R2 rounds with probability P squared, Q squared. But now it's a bit more complicated because we do the same. And at the end, we only evaluate the probability by taking into account all the dependencies between the differential characteristics which shows there. So it's not optimal anymore to do that. And what we proposed at FSE in 2020, I think, 2021, is a model to search for boomerang directly without searching for truncated for differential characteristics before. Okay, so we search directly for boomerang, and we split it into three parts. So first, EMILP model to search for the best truncated boomerang characteristics. So truncated boomerang characteristics. Then a CP model to search for the best instantiation of truncated boomerang characteristics. And finally, an ad hoc tool to evaluate the probability of a boomerang distinguisher. So I will explain a bit more this MILP model for boomerang characteristics and how it works. So first, we need to understand that BCT is only a particular case. And in practice, we have 4 tables, so the BCT and the UBCT, LBCT, EBCT, which actually represent all possible cases of a boomerang through one S-box. And it depends on which differences are fixed and which are are free, okay, and which are zeros as well. And once we have that, it's easy to compute the probability of a boomerang. So here you have some example on Skinny. And so we set some values. So basically, when there is values, this is the values which is fixed at the input or output of the S-box. And when it is gray, it's like we don't really care about the value. So it's completely free. And how we compute this? So basically, here you have one S-box. And here the difference is 0, and the difference here is 0 as well. And so basically, the probability of going from D to 2 and then to 2 to D in on the way back is only the probability of the DDT T2. Okay. Why? Because if it works at the beginning, and then if the difference here is 0 for sure, we know for sure that the difference on the way back will be D and 2 again. Okay. And similarly, here it's a UBCT because we have fixed the transition here, the output of the S-box on the lower trail, but we have this which is completely free. Okay. And so basically, we just need to know which variables are free and which variables are set to a specific value. So this is what we call the controlled. And we can completely compute the number of active S-boxes, at least the number of BCT, the number of UBCT, DDT, etc. Okay, and so our model is very simple. So basically, it's exactly a model to search for differential characteristics. We copy it twice, okay, once for the lower trail and one for the upper trail. And then we just add some new variables to represent whether a variable is controlled or it is free. Okay, and this can give an upper bound on the probability of a boomerang characteristic by looking at a truncated boomerang characteristic. And so we obtained those results for Skinny, which are quite interesting. So what is a bit hard is now to optimize So basically, when we looked at truncated boomerang characteristics, it was easy. The objective was easy. The goal was to minimize the number of active S-boxes. Here we have different kind of active S-boxes, okay, because we have the DDT, the UBCT, the EBCT, okay, and what we want is to optimize not the number of active S-boxes, but the optimal probability they will have. So for Skinny, it's quite easy because basically all those tables have the same probability, and except the BCT, which has probability 1 in the best case. So basically, you just don't count it. And so you only have 2 cases. Either it's one of those tables, or it's a DDT or square. Okay. And we used the Quinn-McCluskey algorithm to reduce the number of inequalities of the model, so to handle the tables and to simplify the whole model. So this is something I will talk about now, reducing the number of inequalities. So basically, when you start implementing some MILP model for a cryptographic problem, you will define some variables and you will say that some of them are impossible. Okay, for instance, I say that I have 4 variables, X, Y, Z, and T. And I say that those 6 values are impossible for X, Y, Z, T. we know how to discard each of them by one equation. And so here we need 6 equations to discard all of them. Okay. Basically, each time, because they are binaries, they are very easy to discard. Okay. Here I just, for the 0, I set the variables, and for the 1, I set 1 minus the variable, and I force that this sum is greater than 1. Okay, because we just created a function for which the minimum is reached only by this value. And so this is a very simple way to describe a lot of cryptographic problems, but it is not really efficient. So basically, we found that the number of inequalities inside the model is highly related to how fast the model will be solved. Okay, and so it's an interesting problem to try to decrease the number of inequalities. So the most known and used algorithm in cryptography will be the Quinn-McCloskey algorithm, which basically search for coset of bit-aligned vector spaces of impossible values. And basically, it will try to group them so we can replace some of the bits by stars, meaning that whatever the values here, this is impossible. Okay. So here I know that if it is impossible that x is equals to 0 and y equals to 0, whatever the values of those two of z and t. Okay. And so using that, we can decrease the number of inequalities to 3 only. So this is very interesting, but the Quinn-McCloskey algorithm is exponential, okay, in the number of variables. And so we cannot run this algorithm to reduce all our model at once. Okay. Typically, it can work for up to 16 or 20 variables. So, okay, then we can use some. So for now, we still have constraints which coefficients are only 0 and 1 because we are only looking at binary variables. But actually, in MILP, we can consider any integers, okay? And we can have coefficients different than 0 and 1. And here we can look at the 2 last equations here. They only differ by 1 variables. And so we can combine them into only one equation. So this way, so x plus y plus 2 times this part, the part in common. And actually, if we have n equals and now there is a question of how we can optimally merge inequalities. And typically, this can be solved using MILP solver. So it's interesting. Okay, so here you have some complexity. So the Quinn-McCloskey algorithm is a big O of 3 to the n. And you have some alternatives. So for instance, in the paper of Bura and Koga, they propose to use balls instead of vector spaces. And so this can be much more efficient depending on the problem. And if the Quinn-McCloskey algorithm is too slow for your program, you can use some heuristic approaches, like for instance, Espresso. And this is a big part when you try to modelize into MILP. To try to find the best representation, the best modelization, and decreasing the number of equations is a big part of the process. Okay, but it's more like an order. Okay, it's not because you removed one equation that then your model will be much faster. Okay, and sometimes removing one equation can make your model slower, but globally, if you decrease the number of equations by 10, by a factor 10, it will probably be much faster. I will continue about those modelization problems. So most of the cryptographers try to provide exact modelization of their problems. Okay. While sometimes it can be interesting and in practice much faster to provide a lossy modelization of our problem, because MILP solvers are not magical. Okay. And if something is hard to solve, it will be hard to solve for the MILP solver as well. And so sometimes it is worth to simplify the problems so it can be solved in a much easier way. So for instance, here I have two variables, x and y, and I assume I have those possible values for x and y. So 0, 0, 0, and 0, 0, 0. So there are treats. I don't know. If I want to correctly describe this, I will need 4 inequalities. So basically an equality on the weight. Okay, here they all have the same weight. The weight of x should be equals to the weight of y, and 3 extra inequalities because here, for instance, I don't have all the possibilities for x equals 1, 0, 0, or for x equals to 0, 1, 1, and for this one as well. And in this case, it can be much faster to remove those 3 inequalities. Basically, they discard only one, each discard only one possible values. Okay, impossible value, and it can be much faster to only keep in the model the equality on the weight and to try those inequalities when you find a solution. Okay? So you have to imagine that this function is applied many times into your model, and so you will save a lot of inequation. Okay, so that's the first idea to provide faster models. Sorry. Another idea is on the other way around. So for instance, here, I have some possible values, 0, 1, 1, and 0, 0 here, which if I want to describe the possible values here, makes this model very complicated. Actually, it will require a lot of inequalities to describe the possible transitions here. But now what I can do is to remove those possible values and to decompose my model into 3 models. So one for which I just have the weight equalities, and 2 other ones for which I have the transitions I didn't add. And it's much more probable that the solutions you are looking for is in the first model than in those 2 ones. So that's interesting as well to if something is very complicated to modelize, is it possible that by adding adding few elements or removing few possible values, can you provide a much more efficient modelization? Okay. And this will be very interesting because, for instance, what is very hard to modelize are DDTs of S boxes. And because it's inherently non-linear, so it requires a lot of inequalities to describe the DDT. But is it possible by slightly modifying the DDT to have a much better modelization of it? And that's an open problem. So actually, we tried with my former PhD student, Baptiste Lambin, to apply those modelization technique to some problem related to division property. And we obtained very good results. So basically, we improved the time complexity, the running time of to find the solution, okay, by using the the techniques are just shown to you. Okay, so for instance, for this particular case on height, our new model takes only 12 minutes, while for the previous one, it took 13 days. So it's quite a huge improvement. And for LED, it's also 3 hours against 16 hours. Okay, 20 seconds against 30 minutes. And so it shows that the modelization of the problem does really affect the time that will be needed to solve the model. Okay, and it is worth to take some time. So I don't know. I think we spend more time improving the model than what we won. We saved, but I think it's interesting. Now we can be faster. Okay, another thing that is important when you develop a MILP model is the branching. So I explained at the beginning of the talk that first, the MILP solver will search for a fractional solution and then choose one variable, which is fractional, and split the model into 2 parts. But actually, so for instance, Gurobi has its own heuristic to select the variables that it will branch on. But in practice, we are much better than Gurobi because cryptographic problems are really structured, and there are variables that are much more important to branch on than others. And actually, for instance, and this is a default of an issue with Gurobi, we cannot choose completely the branching strategy. But for instance, if you are looking for, if you guess some variables at the beginning of a cipher, it's weird to guess some variables at the end of the cipher then. Okay, for instance, you would keep some the variables close together, and this is not something you can force with Gurobi. But in practice, if you change the way Gurobi choose the fractional variables to branch on, you can really improve the running time of the solver. So this is an example of still division property. So what we did is here. So basically, this is monomial prediction. It's some kind of algorithm to okay, so what is the problem? So basically here, you need to find all the possible solutions of a given MILP model. So here, division property was the original model. And the strategy they used in this model was to, they find a solution. Once they find a solution, they fix half of the variables and run a simpler model for all the remaining ones to get all possible solutions this way, and then discard the solution with the found. And they obtain this those running times. Here it's like it's a bit similar, but basically they run the model, and if after sometimes it didn't find a solution, they stop Gurobi, split the model by hand, but by hand they have some algorithm to split the model, but they split the model. They don't let Gurobi touch the model, and start again and again and again. And here we just used the same original model, but instead of using complicated strategies to enumerate all solutions, we just we just tells Gurobi, so there is some functionality. We told Gurobi that this variable is more interesting to branch on than this one. So basically, we sort variables for Gurobi and said, okay, this one is better than this one. And you can see that it is very important. Okay, for instance, for for this number of rounds, it's quite impressive, the timing. So that's also something you can think about, the influence of branching on the strategy. And for instance, if I come back to my simple model for to search for truncated differential characteristics on AES, it is very important to branch on E, actually. And it improves the running time because basically you tell Gurobi that it's better to first know if there is a difference in the column or not. And if there is no difference, you will force zeros. And if there is one difference, he knows that you will add directly 5 S boxes. Okay. And so it's very good to branch on E before branching on the X. Okay, so I talked a lot about tools or about MILP. Now I will talk quickly about objectives. And for that, I will talk about impossible differential cryptanalysis. So basically, in impossible differential cryptanalysis, you use as distinguisher an impossible differential. So basically, here it's not possible to have delta x as input difference and delta y as the output difference. And so if you find a key which by partially encrypting your ciphertext and partially decrypting your ciphertext, you get those differences, you know that the key you used is wrong because it's just not possible. And if you want to compute the complexity of this attack and find the best one, so basically you have many key bits involved in your attack. So you have B key bits, and you need to find a permutation of those key bits. And each time you need to compute the dimension of the number of pairs you will discard. So it's a bit complicated, but it's not really important. What is important here? That the formula of the complexity is this way, where this depends on some linear algebra computation on the dimension of some subspaces. And here it's the same, because it's the entropy of the first E key bits you computed. And you see that this formula is very complicated. And if you want to find the best permutation sigma to optimize your attack, it's very complicated. Here, it seems that we have no other possibilities than exhausting all the possible sigmas. Okay? And it's impossible to do that. In this case, when the objective is too complicated to compute, we can use approximation. And for instance, at Indocrypt 14, Boura, Naya Plasencia, and Souder propose the formula, an approximation of this formula, which is this one, and which does not depend on sigma. And actually, it is only the terms here of this equation which does not depend on sigma. So the term 0 and b. And so this is a lower bound. But now with this approximation, we have an objective to optimize, an objective simple enough to be computed, and we can search for the best impossible differential attacks. Another example for which the objective was very hard is boomerang attacks. So very recently, I proposed a new model to search for boomerang attacks against AES. But if you want to compute the complexity of a boomerang attacks on AES, it requires to compute the dimension of many of several stuff and to compute the entropy of some key bytes, and it's very complicated. And so basically, to search for the best boomerang attacks against AES, we only search for the best boomerang patterns, and we add an objective which is related to our intuition. Basically, so there is the probability of the distinguisher. This is something we can compute. But then we only assume that it is better if the difference in the plain text and ciphertext are known than if they are unknown. And so we were able to rank patterns, and we have a good, we expect that ranking patterns is equivalent to ranking attacks. And actually, doing that allowed us to find a new boomerang attacks against full AES 192, which is 2 to the 40 times faster than the previous one presented by Biryukov and Kovatovich. Okay, so it's very important. So finally, we have many open problems in modelizations and in algorithms. So it's still unclear how to provide the modelization that will be the best one, that will be solved very in the faster way. It is also unclear why MILP solvers seems to outperform SAT and CP solvers for cryptographic related problems. Well, that's only my experience. So maybe here some people are much stronger than me with SAT and CP and get a much better running time. But I think my experience shows that for cryptographic related problems, even the ones that only involves binary variables, it seems that MILP is much faster. But the issue with using MILP solvers or SAT solvers or CP solvers is that basically we don't really understand why we obtain a result, and we don't really understand the complexity of what we are doing. Okay, and so if it works, and we are happy. But if it does not, we don't know if we are very far to get a solution or not. And sometimes I think it's interesting to get algorithms, ad hoc algorithms that we fully understand and for which we can estimate the complexity to search for best attacks. It will be interesting. And today in this talk, I only talked about cryptanalysis, but there is something much harder than cryptanalysis, and this is using MILP or using tools to automatically design optimal components for block cipher or whatever. Okay, thank you for your attention. Yes. Yeah. This one? No. Okay, Samsung. Okay, that's right. Yeah. It's a very complicated question. Actually, I don't know. It's a good question. I think it should be possible, but do you have a precise example? Yes. Okay. No, no, no. No, no, no. It does not guarantee to be faster, but it depends. Actually, it depends. Uh, if you start with a model with I don't know 1,000 equations, and then you can reduce them and get 100 equations, maybe it will be much faster. But if you have a model with 100 equations and then you reduce it to 99 equations, it will not really be faster. It can be very slower. So it's like magnitude only. And it's unclear. For instance, I'm sure it's possible to find a representation with 1,000 equations, which is faster than a model with 100 equations. But in practice, we constate that if we can decrease the number of equations, it's better. But it depends. You should do that without introducing not too many new variables. So it's a trade-off. Yeah, as well. Yes. But it depends because usually when you remove variables, you will have many more constraints. So it's really a trade-off and it's hard to find the best possible modelization. Right. Yes. 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 I don't know. It depends. On this one, indeed, it can lead to wrong solutions because we removed those constraints. And actually, in this case, we will just add them into a callback. So basically, each time the solver finds a solution, you will check those constraints. And if it is required to discard the solution, you will add it to the model, but only if it discards the optimal solution. Okay. And so in practice, it does not happen very often. But here it's more complicated here because here you will search for the solution here, and you don't have wrong solutions, but you didn't explore all possible solutions. But what you may expect here is that you will get a bound in a faster way than if you had to describe exactly the model. So you have a good approximation of the optimal solution and probably already the optimal solution. And then in the exact model, you already start with a good solution and you will search a better one. So you expect that it will be faster. Yes. Yes. So actually, we capture all the dependencies. Yes, I see. No, we don't capture all dependency because we still assume independence between rounds. And for instance, on Skinny, it does not work, I think. Because there are many keys for which there is no solutions and stuff like this. Yeah. Not for Skinny, for instance. If you don't. Yeah, I think so. Yes. We have all cases. Okay, so maybe we should write something in a much formal way. Thank you.
পিওর ম্যাথস এর স্টুডেন্টরা ক্যালকাটা কলকাতা আমাদের এই ক্যামেরাটা নিয়ে যাচ্ছি আর শুধু ডান্ডিটা রেখে যাচ্ছি। হ্যাঁ এটা রেখে যাই কালকে, অসুবিধা নেই তো? হ্যাঁ ঠিক আছে, থাকুন তাহলে।